Hello and welcome everyone, this is Priyanka, and in this session we are going to talk about abnormal colligative properties. Before talking about abnormal colligative properties, let's have a quick review at what exactly do we understand by colligative properties. Colligative properties, as we all know, are the properties of the solution which depend only on the number of solute particles present in the solution, and they are completely independent of nature or the composition of solute particles. You must note that the solute particles which we are studying here are non-electrolytic, non-volatile and non-associated in nature. There are 4 colligative properties in total. Relative lowering of vapor pressure, which is P01 minus P divided by P01, which is equal to X2, which is the mole fraction of solute. The second colligative property was elevation in boiling point, for which we found the expression delta TB is equal to Kb multiplied by M, where Kb was ebullioscopic constant, M was the molality of the solution. The third colligative property was depression in freezing point, for which we found the expression delta Tf was equal to Kf multiplied by M, where Kf was the cryoscopic constant. And the final colligative property that we had studied was osmotic pressure, for which we found the expression pi, which is osmotic pressure, was equal to N2 by V multiplied by RT. Now again we are going to repeat that the solute particles which we had added in the solution while non-electrolytic, non-volatile and non-associated solute. Now let's understand what happens when the solute is electrolytic or when the solute is volatile. Now in that case the solute may undergo dissociation or association. As you can see, in the first case there is dissociation of solute particles. So what exactly do we understand by dissociation? If you have a solute particle which is represented by AB, that solute is going to be dissociated into its constituent ions, which is A plus and B minus. And hence in this case, the number of solute particles after being dissolved in the solvent are going to increase in case of dissociation. As you can see in the second diagram, we are studying association of solute particles. What is happening here is the number of solute particles are coming together and forming a polymer. In this case, we are considering a solute particle represented by AB. N number of particles will come together and form a polymer. And hence, the number of solute particles are going to decrease in case of association. Now, let's study each of these phenomena in detail. Let's start with dissociation first. Take an example of NaCl, which is sodium chloride. Assume that you've taken 1 mole of sodium chloride and you dissolve it in some amount of water. Now what happens is, once this 1 mole of sodium chloride is dissolved in water, the ions are going to be formed. So the solute particle, the solute molecule is going to be broken down into its constituent ions, which is Na plus and Cl minus. So initially we had taken 1 mole of solute, that is going to be dissolved into 1 mole of Na plus and 1 mole of Cl minus, which in turn is giving you 2 moles in total. As you can see, 1 mole is giving 2 moles, so there is increase in number of moles of solute particles. We know that colligative properties are directly proportional to the number of solute particles. In dissociation, the number of solute particles are increasing. There is going to be increase in value of colligative property as well. Also, it is experimentally found that molar mass is inversely proportional to the colligative property. And hence, when we are using an ionic solute, in which case there is going to be dissociation, the observed value of molar mass will always be less than the theoretical value of molar mass of the solute. And hence, in this case, the theoretical molar mass of sodium chloride, as we all know, is 58.5 gram. The observed value of molar mass of sodium chloride will be exactly half of the theoretical value, because 1 mole got dissociated in 2 moles. So molar mass will be half of the real value, which is 58.5, and hence the observed molecular mass of NaCl is found to be 29.25 gram. Now that we are clear with the concept of dissociation of solute particles, let's try and understand what happens in case of association of solute particles. For that, we are considering an example in which acetic acid is dissolved in benzene. Let's try and understand what happens when acetic acid is dissolved in benzene. In this case, acetic acid is going to form a dimer. That means 2 moles of acetic acid are going to combine together to form a single molecule, which is acetic acid dimer. And hence, in this case, there is going to be decrease in total number of moles of solute particles. Now, as you all know that the colligative property is directly proportional to the number of solute particles present in the solution, and in case of association, the number of solute particles are being decreased, and so the value of colligative property will also decrease. As we all know that molecular mass of a solute is inversely proportional to its colligative property, and hence in case of association, observed molecular mass will always be greater than the theoretical molecular mass of the solute. In this case, we have considered acetic acid, of which the molecular mass is 60 gram, and observed mass, since 2 moles of acetic acid combined and form 1 mole of acetic acid, the observed molecular mass will be double than the original molecular mass, and hence we know that the molecular mass of acetic acid, the theoretical molecular mass is 60 gram, the observed molecular mass is going to be double of that, and hence you will get 120 gram as the molecular mass of acetic acid. To generalize this entire phenomenon, a scientist called Van't Hoff proposed a factor which is called as Van't Hoff factor. The factor is also called as I, which is equal to the observed colligative property divided by theoretical colligative property. Now, as we all know that colligative property is inversely proportional to molecular mass, this formula can also be written as theoretical molecular mass of solute divided by observed molecular mass of solute. Now, depending on the 3 different kinds of solute particles that can be added in the solvent to form a solution, I can assume 3 different values. Now, let's study that in detail. So, the value of I will be equal to 1 when there is no dissociation or association taking place of solute molecules. So, when there is no change in the number of solute molecules present in the solution, the observed value and theoretical value of the colligative property is going to remain same, and hence I will be equal to 1. Now, the best example that we can take is glucose added in water, or urea, or simply sugar added in water, which is non-electrolyte, and hence there is no dissociation or association taking place. Now, the second case that we have, when there is dissociation of solute particles taking place. Now, what is happening is there is the observed colligative property will be more than the theoretical colligative property, because of which I will be greater than 1. And the simplest example is NaCl added in water, or any ionic solid added in water. The third and the final value of I will be less than 1. Simplest example is acetic acid added in benzene, wherein there is association taking place, and hence the observed value is going to be less than the theoretical value, for which I is going to be less than 1. With this, we have completed the abnormal colligative properties. I hope you found this video useful. If you did, please hit the like button and subscribe to our channel. Thank you for watching.